And we're back. Welcome to our next video for section 7.5. This is the back of the notes. You should have already completed the front part. Now we're going to talk a little bit about how to identify if a function is exponential, okay? And part of how we're going to do this is we're going to compare it to the other type of function that we've studied this year, which is the linear function. So if we think about a linear function, right? Linear goes in this first box. The equation we should all remember for a linear function is the good old-fashioned slope-intercept form. Y equals mx plus b. Never let yourself forget y equals mx plus b. Anytime you see any equation with some number times x plus some other number or minus some other number, you know you're dealing with a line. That is a linear equation. When you graph it, you will have your x and y axis and some form of a straight line, okay? Going on forever and ever in both directions. The domain is all real numbers. The range is all real numbers. That's our linear function, okay? The thing that we haven't talked a ton about, although we have talked a little bit about it, is what it looks like in a table, okay? And most of the tables we deal with in these problems will be horizontal, so you'll have your x's and your y's, x's on top, y's on the bottom. And you know, your x's will usually go up by 1, so it'll be something like, I don't know, 0, 1, 2, and 3, just as an example. And then for an example for the y values, you know, there'll be something like -3, 0, 3, 6. And the way that we can look at this table and say, oh, that's linear, is we actually look at the y values. And we want to notice how they change from each x value, right? So when we take this first step, I ask myself the question, okay, how do I get from -3 to 0? And the answer is, well, I just add 3. And then how do I get from 0 to 3? Well, I add 3 again. And how do I get from 3 to 6? I add 3. The fact that I keep adding the same number, we call that a constant rate of change. And you might want to write that off to the side. It's a good vocabulary word to have, constant rate of change. And for those of you who are really paying attention, you'll remember that that's also our definition for a slope. Slope of a line is its constant rate of change. So if I look at the table and I see the y values and they keep increasing at the same rate for every single x increment, then I know I've got a linear function. Now, the new guy on the block then is this exponential, okay? Exponential, down in this box, exponential function. That, as we talked about in the previous video, y equals a b to the x, okay? That's our standard form for a basic exponential function. And, you know, we have more complicated versions of it that we'll get into later, but this is the gist of it. Anything that looks like, anything that's got that x value as the exponent, that's an exponential function, all right? Now, we also talked a little bit about how the graph usually will look like this. Start off flat on the left and then spike up, or, and I've got multiple pins so I can do this in different colors, it'll start high and then flatten out to the right. Those are our two most basic exponential functions that we're going to see, okay? But again, the new thing that I want you to see in this video is how to look at the table and identify it. So let's make a table similar to what we did in the last example, right? X on the top, Y on the bottom. And we'll change our X values up because these don't matter, so I just want you to see that. Let's have -4, -3, -2, and -1. And then for my Y values, I'm going to have something like 1, 2, 4, and 8, okay? Now, if we think about the previous example, right, we said, okay, how did I get from -3 to 0? Oh, I just add 3, and then I add 3 again to get to 3, and I add 3 again to get to 6. But here, if I try and do this with addition, I would add 1 to get to 2, but then I'd have to add 2 to get to 4, and I'd have to add 4 to get to 8. I can't just add the same number here each time. So I then have to think, okay, well, how else could I get from 1 to 2? Well, I could multiply 1 by 2, because we know 1 times 2 is 2. And then if I take 2 and I multiply it by 2, well, that's 4. And if I multiply 4 by 2, sorry, this got so weird and uneven. It almost looks like an exponential curve, but in the opposite direction. Haha. Anyway, multiply by 2, and I get 8. So what I notice here is that instead of having this constant rate of change, I have something that's called a common ratio. Okay? Oops, that's ration. Pardon me. Ratio. Remember, ratio means fraction. And the reason that we say common fraction is because if I work backwards on these problems, which can be really helpful if I can't figure out what the pattern is, if I just work backwards, instead of saying what do I multiply by, I think about a ratio, and so I divide. And what is 8 divided by 4? 2. What's 4 divided by 2? 2. What's 2 divided by 1? 2. And this would keep going. I would start getting decimals. If I went in this direction, I'd get 16 and 32 and even bigger numbers after that if I went in this direction. That pattern would maintain itself, and that's where this common ratio comes from. So what we're going to be doing in these next sets of problems, and there's only about 4 or 6 of them on the homework, but what we're going to do is we're going to be looking at it, and we have to say, okay, is this data exponential behavior? Do I have a common ratio, or do I have something else? So if we look at number 1, I say, okay, well, how would I get from 5 to 10? And how would I get from 10 to 15? And how would I get from 15 to 20? Now, if we're looking for exponential, I think, oh, okay, well, 5 times 2 is 10. But 10 times 2 is not 15, and 15 times 2 is not 20. In fact, I imagine a lot of you look at this and you go, oh, this is just plus 5, plus 5, plus 5. Do you guys see that pattern, how it develops there? So this one would be linear, but the question is asking, is it exponential or not? Right, yes or no. For this one, we would simply write, no, it's not, okay? If you're looking for bonus points, yeah, tell me it's linear, but this is what I need, okay? When it says explain why or why not, you could say it's linear. You could show that it's plus 5, plus 5, plus 5, okay? Or you could explain that there's no common ratio. No common ratio. However you want to show me, explain why or why not, that's like the showing your work part of this, okay? The key thing is, can you identify that it's not exponential, and then give me some kind of evidence that makes me know, oh yeah, this person knows what they're talking about. Now for number 2, again, the x values really don't matter, but 3, 9, 27, 81. Okay, a lot of you looking at that right away and going, well, that's not linear. 3 plus 6, 9 plus, what is that, 18, I think? Yuck. Point is, it's definitely not a common ratio, but 3 times 3 is 9. 9 times 3 is 27, and maybe you can't do it in your head, but check it in your calculator real quick. 27 times 3 is, you guessed it, 81. So here I do have times 3 times 3 times 3. That's my common ratio, so I would be able to say, yes, this is exponential. And again, you've got lots of different ways you can say it. You've already kind of shown this. That'll be enough for a quiz. But if you want to go ahead and add on that there is a common ratio of 3, good. You're a step ahead of us. Okay? Take a minute, pause the video, try number 3, and see what you come up with. Okay. 3 is tricky because it's definitely not adding the same thing over and over again. The numbers are actually getting smaller. But we know that a common rate of change can be negative because we know that a slope can be negative. But even still, I could do 32 minus 16 to get to 16. But then if I subtract 16 again, that doesn't give me 8. So it's still not going to be linear. So now I have to say, okay, well, what is this common ratio? What am I going to multiply 32 by to get to 16? Some of you who are especially good at recognizing patterns probably looked at it and said, wait a minute, couldn't I just divide by 2 each time? Isn't 32 divided by 2 16? 16 divided by 2 is 8. 8 divided by 2 is 4. Yes, yes, it absolutely is. That's correct. But since we call it common ratio, I like to think of it as, instead of dividing by 2, I'm actually multiplying by 1/2, okay? Because what's 1/2 of 32? Oh, it's 16. And what's 1/2 of 16? Oh, it's 8. And 1/2 of 8 is 4. And if I kept going, I'd have 1/2 of 4 is 2, and 1/2 of 2 is 1, and that pattern would keep going. So this is yes, because it has a common ratio of 1/2. Now, I'll take a quick break and remind you, if you're ever stuck finding a pattern, you can always work backwards, okay? I can't figure out what I'm supposed to multiply by to get these numbers. Well, then start at the other end. 4 divided by 8 is 1/2. And 8 divided by 16 is 1/2. 16 divided by 32 is 1/2. If you can't just look at it and figure it out, work your way backwards. Work your way backwards and you'll get the common ratio that we're looking for, okay? Now, 4 is tricky, okay? Because look at the y values. How do I get from 3 to 3, 3 to 3, 3 to 3? The 3 is all the same. Now, if we think about this, if you could picture this graph, right, this is going to be a horizontal line because the y values, if this is my y-axis, right, 1, 2, 3, that's what we're looking at. We're looking at a horizontal line that goes through 3. So is this exponential? No, it's not. It's not exponential because it forms a horizontal line, okay? Now, what some kids will tell me, though, is they'll say, yeah, Mr. Young, sure, you could say that you're doing plus 0, plus 0, plus 0, plus 0. But they'll say, aren't you also doing times 1, times 1, times 1? And you're right, you are. But there's a rule with exponential equations that says that b, that common ratio, that rate of change for an exponential function, can't be 1. Because if b is 1, then it's a line. It's no longer an exponential curve. So anytime you have a plus 0 situation, it's linear. It's going to form a line, okay? Now, these next two, I don't want you to freak out about these, okay? They're just decimals. And again, if you can't look at 1 and 0.5 and 0.5 and 0.25 and say, oh yeah, that's just times a half again, don't worry about it. You're not alone. Instead, work backwards. Let your calculator do the hard work for you, okay? Try it out. Turn it on, of course. Clear it out. Go home. There we go. 0.125 divided by 0.25 is 0.5, which math, fraction, enter, it's 1/2. So you see right there, we get that 1/2 again. If I check it again to make sure it's common, 0.25 divided by 0.5, it's 0.5 again, which we know, oops, math, enter, is 1/2, okay? So just by working backwards, I can see pretty quickly times 1/2, times 1/2, times 1/2. And if I have that repeated multiplication or even really repeated division, it's the same thing. I know that, yes, it's exponential. You try 6, you're going to get the same response, right? In this case, you're going to be doing times 1/3 each time. Okay, I'll just kind of give you the answer there, and you can check that on your own, all right? So that's what we're doing for these last chunk of homework problems. You're looking at the table, and you're saying, is there a common ratio, or is there a common rate of change, constant rate of change? The answer is going to tell you if it's exponential or not, all right? So finish those last 4 on the front, and then once you're done with those, make sure you do those extra graphs in the back, and then by the grace of God, I will see you guys very soon. I love you and thank you for watching. Again, if you have questions, do not hesitate to write them down. Get a hold of me through Remind. I should be available for most of the day. And I should be back soon so we can answer your questions. All right, thank you.